Okay, so let's continue our discussion on batch distillation. So in our previous lecture, we have talked about differential distillation. That's the simplest case, in which we have our distill pot has no reflux drum and has no rectifying section. Then we introduced um, the batch distillation with a rectifying and a reflux drum, which can improve the separation outcome. And we talk about there are two operation modes for this batch distillation with a rectifier section, right? And we talk about uh, how do we analyze a constant reflux ratio operation in which the reflux ratio is maintained as a constant. That means for a fixed V, right, fixed boil-up ratio, a boil-up for a fixed boil-up flow rate, the amount of after the overhead vapor going into the condenser and becomes a liquid, then for a constant reflux ratio, the amount of the liquid that's being returned back to the tower is a constant. Okay, so that the distillate flow rate is also a constant. In this case, because your still pot composition is decreasing, then your distillate composition is also decreasing, right? And so it's easy to do, but it's hard to control so because the distillate composition is decreasing, then once we finish the distillation, the average distillate composition is going to be a basically decreasing function of time, right? So longer you operate your batch distillator, the lower average distillate composition you have. Okay. Then we talk about if you want to achieve a constant distillate composition as in the operation of constant distillate composition operation, we have to adjust the reflux ratio, right? We have to adjust reflux ratio. So just to deal with as the XW goes down, we basically have to increase the amount of liquid being returned back to the column to maintain the same distillate composition. Okay. Now today we're going to analyze. You're going to introduce how we analyze this type of operation. Okay. So here, xt is known and it's a specified constant, and v is typically a constant, right? So we can control the amount of vapor being produced from the residue to be a constant. Now in this case, we need to decrease L over V to make sure accordingly as XW goes down to make sure XD is a constant, right? So if we start from the average distillate composition, right, we know the average distillate composition is basically how much light K is being is being produced in the distillate, right? That's initial. This gives you initial amount of light K in your residue in your still pot, and this gives you the amount of light K in your still pot at time t, and the difference gives you how much light K is present in your distillate, and this gives you basically how much mixture you have, you have distillated, right? How much mixture that has left the whole process as a product. So this gives you the average composition for your distillate. For a constant distillate composition operation, XD is not changing with time, right? So XD is just a constant, so we can just drop off average here. And we just use XD to denote it. Then you can rewrite this whole equation so that W is a function of W0, XD, XW0, and XW, right? So here, basically, XD is given, XW0 is given, W0 is given, right? So they are basically the initial condition of your steel part, as well as your desired separation outcome. Then from this equation, we can tell W is going to be a function of XW. Both of them decrease with time. If we take the derivative on both hand side, right? On the left-hand side, we take a derivative of dW with respect to t. On the right-hand side, we take the derivative with respect to, also with respect to t. In this case, on the right-hand side, only xw is changing, right? Then we can get this, because xw is on the basically denominator. So we have a square here. Then minus sign here give you a minus here. That will basically cancel the, cancel out. So we have a kind of positive term here. Now, because dw dt is equals minus d, right? dw dt is basically equals to the distillate rate, minus distillate rate, right? So, and the d is v minus L. So we can just write down minus dw over dt equals v minus L. Now we can just plug in dw dt back here. So we have minus bracket v minus L on the left-hand side, right? Now if we take dt to the left, then we can integrate this whole equation on both left-hand side and right-hand side. On the left-hand side, we move dt to the left, and then we move v minus L to the right-hand side. And left-hand side is integral of dt that gives us t. On the right-hand side, W0 is a constant, XD is a constant, XW0 is constant, and V is a constant, right? So we can take them out, right? Then we can just integrate this whole term here. So basically, we have dxw there. We have xd minus xw squared there, right? So we have, now we moved V minus L, well, actually minus V, minus bracket V minus L to the right-hand side. Now we take V out, so we have 1 minus L over V, right? Left inside of the bracket. Okay, so where does the minus sign go? Note here, for t, we basically integrate from time 0 to time t, so which is basically t. We absorb the minus sign here, right? So we integrate basically from xw, that's the composition of the steel part at time t, and xw0, that's the composition of the steel part at time 0, right? So basically, that absorbs the minus sign, right? Because basically for t here, we integrate from time 0 to time t. Here, we integrate from time t, the composition at time t to the composition at time 0. Okay, that's how where the minus sign is absorbed. Now, if we examine this equation, we know that W0 and XW0, those are the initial conditions for your steel part. They are known. XT is the desired separation, distillation outcome. This is specified. And V is basically the molar flow rate leaving the steel part. And that's also a constant. And inside, XT is constant, right? XW basically decrease with time. Correspondingly, L has to increase with time, right? So this whole term basically change with time, and it change with XW. So in order to compute T, we have to basically figure out at different XW, we have to figure out L over V, right? So what is L over V? The L over V is basically the slope of the rectifying section operating line on the McKibbe-Tilly method diagram. Okay, so with that, that basically reminds of us that we can actually use the McKibbe-Tilly diagram to find the value, of L over V at different XW, right? Then we have the value of this whole function. Then we can do this integral numerically. Okay, so how do we do that? Let's look at the McKibbe-Tilly diagram. So here, let's say we wanna solve this equation. Especially we want to solve this integral. Then to solve this integral, we have to get basically the values for this whole function. 1 over 1 minus L over V bracket multiplied by this xt minus xw squared, right? We need to know the value of that function. To do that, we need to know the value of L over V at different xw. So to do this, we can choose an xw, right? For example, xw1 here. Then we need to construct an operating line with such that in NT stages, we hit the intersection of the operating line and the 45-degree line, right? This defines R for the choosing XW in step 1, right? So basically, what that means is once you pick XW1, right, and XD is fixed, right? Basically, we can do the step of operation with once an operating line is given, right? If for example, if our system has 4 stages, then we need to, starting from XW1, we need to reach XD in 4 stages, right? We have to reach that point, exact point in 4 stages, right? We explained why we have to do that in our last lecture. Okay. So once you find out the operating line, that can exactly help you to achieve, start from XW1 and at XD, then we can read off the slope of that operating line. Then you can compute, and the slope of that operating line gives you L over V, right? Now you have your value of L over V from the slope of the operating line, and you have XW, which is specified, right, in your analysis. Then you get the value of this function, right? Now you can repeat steps 1 to 2 for different values of XW in the desired range, right, until you have enough points, right? Then you can just basically make a table of, with kind of two rows. The first row has XW at different values. The second row has the value of this function. Then you can do a numerical integration using traploid rule to find T for a given XW. Okay. Now let's look at an example, how we do that. So here we have a 3-stage batch still. That means we have a boiler and we have equivalent of 2 equilibrium plates that is loaded with 100 mole of a liquid containing a mixture of 50% hexane in octane, right? So we know the initial W0 to be 100 kilomole, and the XW0 is 0.5. A liquid distillate of 0.9 mole fraction of hexane is to be maintained by continuously adjusting the reflux ratio, right? That means XT is 0.9, while maintaining a distillate rate of 20 kilomole per hour. That means V is, that means D is 20 kilomole per hour. Oh, sorry, like that means V is 20 kilomole. Oh, sorry, that's D is 20 kilomole per hour. Okay, so what should the reflux ratio be after 1 hour when the accumulated distillate is 20 kilomole, right? Well, to answer that question, basically we know after 1 hour, and we can compute the W after 1 hour, right? And from that we can compute the XW after 1 hour, right? Now we have XW, and we can use the McKibbe-Tilly diagram to find out the slope of the operating line. Then from that we can compute the reflux ratio, right? That's basically how we're going to solve this problem. To do that, we need to find out XD and XW, right? XD is given 0.9, right? That's given in the problem statement. And for XW, we need to compute it. So how do we do that? We start from this equation that relates basically W with XW, right? So in this whole equation, we know W0, that's 100. We know XD, that's 0.9. Okay. We know XW0, that's 0.5, right? So we also know W, right? Because we've been distillating for 1 hour. So we start from 100 kilomole, and 20 kilomole is left. So we have 80 kilomole left. Okay, left in the still pot. So we can rearrange this equation. We have XW to be a function of W XD, W0, and XW0. Now you can plug in the numbers. So XD is 0.9, W is 80, right? Because we start from 100, and the 20 left. 20 left the still pot, minus W0, that's 100, multiplied by bracket XD, that's 0.9, minus XW0, and that's 0.5, right? Divided by 80. That gives us 0.4. Okay, so now we can mark the point. We have 0.4. That's the still composition after 1 hour of distillation. Next thing we do is to find the operating line that basically with 3 stages, right? This is a 3-stage batch still with 3 stages. We can start from XW, right? Then end exactly at XD at this point. So the way we can do that is, for example, we have to do this by trial and error. For example, if we randomly pick a operating line to start with, right? Now, there are 2 ways you can do the rest. One way is that you can basically start from 0.4, that's the XW value, and doing the step off, right? So just go upward, hitting the equilibrium line, and going horizontally, and do this back and forth, and see after 3 stages, do you converge at this point, right? That's one way to do that. Another way you can do this is start from the other end, start from XD, right? Now I do step off with 3 stages, right? I start from there. I do this 1 stage, 2 stage, and the 3 stages, right? Now I can get a XW value from after this 3-stage operation. That's going to be something around 1.16 or 0.17, right? As we can see, this is much lower than XW, the overcomputed XW. That means this operating line is too steep, right? We need to basically, using that point as a rotating point, evolving center, we need to basically, pull this operating line up, right? Until at some point, right? If you do the step off after 3 stages, we hit exactly XW equals 0.4, right? So the kind of solution is already given in this diagram by line 9.1. Okay. And then we can read off the slope of this line just by measuring, you know, if you draw a horizontal line here and draw a vertical line here, and so they will basically cross at one point. Then you can measure the length of the vertical drop down. You can also measure the length of this horizontal line segment. Then the ratio gives you the slope, right? So here, the slope is 0.22 for this problem. And with that, we can compute the reflex ratio, right? Just remember that the L over V is related to reflex ratio by this equation. Then you just rearrange this equation. So you can have reflex ratio to be dependent on L over V by this equation. Plug in the numbers, we get a reflex ratio of 0.282, right? So we solved the first question of this problem. Now the second question is, theoretically, when must distillate accumulation be stopped, right? So what does this mean? Recall that to maintain a constant distillate composition, we have to increase the amount of the liquid being returned back to the tower, right? From the reflux drum, from the condenser. We have to increase the amount of liquid being returned back to the tower. But there's an upper limit we can do that, right? When that upper limit is basically L equals V, right? L equals V, right? When that happens, basically we cannot further increase the reflux ratio. We have reached the maximum reflux ratio we can do, right? So in that case, L equals V, so L over V is 1. L over V is basically the slope of the operating line. That means in that scenario, we reach the scenario of so-called total reflux, right? We've talked about this we have discussed this in our limiting cases of distillation operation. So that's when we have to stop our distillate operation if we still want to maintain our distillate composition to be invariant, right? We can still continue to do the still operation after that time, after that point, but we just cannot maintain the distillate composition to be the same, okay? So basically, once we reach total reflux, because we cannot further increase the reflux ratio, then either we have to stop there so that in the whole process, our distillate composition is constant, right? It's a constant as we specified in our design, or if we continue to operate the distillation because we cannot further increase the reflux ratio, then the distillate composition has to drop, you know, after that particular point, particular time. Okay, then for the total reflux scenario, right, if we do the step off from XD with 3 stages, right, stage 1, 2, and 3, we can find out the XW, right? That's basically the still pot composition, which is 0.06. Then we can compute the time it takes for us to reach this still pot composition, right? We can just do that by analyzing the light-K mole balance by the light-K mole balance, right? How do we do that? Okay. So let's see if it takes time t for us to reach that still composition of 0.006. Then at time t, we start from 100 kilomole, and we have basically and 20 multiplied by t, that amount of mixture has left the still pot, right? This is what we have left. Okay, then you multiply by the composition. This gives you how much leachate we have left in the still pot. Okay. On the right hand side, 50, that's basically 50 more percent multiplied by 100. That's how much we have, how much leachate we have in the still pot at the beginning. Minus, and this term gives you how much leachate has left the still pot, right? So we have 20 multiplied by T, that's basically how much mixture that has left the still pot, multiplied by the distillate composition 0.9. This gives you how much leachate has left your still pot, right? So basically, then we have basically on the left-hand side, how much leachate is left in the still pot, and right-hand side, we also have the how much leachate is left in the still pot, right? Then we can just solve this equation. We'll get T equals 2.58 hours. Right? That's the time it takes basically that's the time it takes to drop the still pot composition from 50% to 6%, right? Then we reach total reflux. Then we have to stop if we still want to keep the distillate composition to be invariant, to be constant. Okay. Okay, that's the second example for this lecture.